In this video, we are going to discuss compensation theorem. Let's see. So theorem. So we were discussing network theorems, and today we are going to do one more new theorem, which is compensation theorem. So what we will do, we will first state the theorem and understand what it says, how to apply it. Okay, so state, and so we'll learn how to apply it, or when to apply it. We'll learn that. Okay, then we will do proof. And you know that for practitioners, those who practice electrical engineering, for them to know how to apply a theorem is more important, is more important than knowing how to prove it. But proofs, definitely, on the other hand, are very important. Those who want to continue research, so for them proofs are important. These are basically a kind of exercise for the researchers. And particularly in this course, I know that there is a large number of students from computer science. Okay, and I know I was in computer science for a while, and so I know that they do subjects like algorithms, where they do a lot of proofs, and that's what they love. And since almost half of the students in this class are from computer science, we will do proofs. And this is, I know, is very fun, is a fun for them. So we will do actually 3 different proofs. Okay, so the first one we will do using substitution theorem. Second one is also using substitution theorem. Almost similar. These two are almost similar. This one is in your notes. This is slightly different, but this will actually highlight the naming of this theorem, why this is called a compensation theorem. So naming will be justified. And the third one I will use Thevenin theorem. So I'll use this. So I'll use Thevenin's theorem for the third proof, third alternative proof, and this I believe is the easiest to remember. And proofs are also useful for, I mean, if by chance if you forget the statement, if you know the proof, you can recall or you can reformulate the statement yourselves. So that's why knowing the proofs are also useful, even for the practitioners, even for non-researchers. Okay, and this one will be, in my belief, according to my belief, will be the easiest to remember. So that's why I will do it at the end. Okay. Because if I do it fast, you won't look for the other proofs, I know. Okay, cool. So we shall start with the statement, or how to apply. So it says that if I have a network, complicated network, which has internal sources like current sources and voltage sources internally, and then there is one particular branch which is of particular interest, where we have a load connected and the load impedance is ZL. What we are interested in to find IL, or this current I. Okay. let me just use I. Let me just use Z for shorthand. Okay, so the goal or the target is to find I. So for that we have to solve this network. We have to use some method for that. But suppose this is solved. Suppose this is already solved once, and then we change the load, that means load impedance, from Z to Z plus delta Z. Okay, suppose I have already solved this network once with this impedance as Z, and then I change this from Z to Z plus delta Z. This becomes Z plus delta Z. So definitely this current will change. So this will become I plus delta I. If you are thinking that it should be I minus delta I, assuming this as resistive, no problem. Delta I could be negative, or it could be actually, this could be phasors, this could be Laplace domain impedances, doesn't matter. So this is just a symbol, I plus delta I. So I changes from I plus delta I when Z is changed from Z plus delta Z. Now the question is, this is equal to what? Z plus delta Z is given, so this is given, and this is the unknown. Now what we can do? Should we solve again? Yeah, one way is, of course, definitely we can solve the entire circuit once again, but sometimes it's not, but sometimes it's it could be easier to use this compensation theorem to find this new solution more easily than solving the entire circuit once again. Okay, so solving it, not necessary. So we can use compensation theorem to find the new value of this current I plus delta I when this impedance is changed from Z plus delta Z. Okay, so that's the situation. So we have solved this circuit once with impedance equal to Z. So suppose that this is already solved for Z. Okay, so this is, suppose this is already solved once for impedance equal to Z, and now we change the impedance from Z to Z plus delta Z. We do not have to solve it once again. We can use compensation theorem. How? Okay. So compensation theorem says that when this becomes Z plus delta Z, you apply a source, okay, like this, call it V, which is equal to delta Z times I, and what is I? Where I was the current, original current when impedance was equal to Z. So that current, so that I multiplied by delta Z, take this voltage source, connect it in series with Z plus delta Z as shown here. Okay, and in this circuit you remove deactivate all the sources. So current sources are opened and voltage sources are shorted. Okay, so do this. Remember this. So this impedance, remember that this impedance is the new impedance. So remember this, that this is the new impedance. This current is the old current. And this network is deactivated network. So all the sources are turned off. Now solve this circuit. Okay, if you solve this circuit, the current that we will have here is equal to delta I. Okay, so that's what compensation theorem is. Let me restate the situation. The situation is that I have a network and I'm interested to find the current in one particular branch. I have solved it already once with a particular value of Z, but then for some reason I have to change this impedance from Z to Z plus delta Z. Suppose this was a motor, I change the motor, so its impedance changes, and then I want to compute the new current, which will be some old current plus some change, I plus delta I, and I want to find what this value is. I do not have to solve it once again. Instead, I do not have to solve the original circuit once again. Instead, I can solve this circuit where all the internal sources are deactivated and the external part is modified as follows. So I use the new impedance Z plus delta Z and a voltage source which is delta Z times I, where I is the old current, and I solve this, I will get delta I. Is it easier? You might be thinking, is this easier? Is this particular scheme is easier than the original circuit, than solving the original circuit? It could be, no? It could be sometimes, because say I want to solve this original circuit once again from the scratch, and suppose I apply superposition theorem on this, right? Suppose I use superposition theorem on this. Suppose I use superposition on the original circuit with Z plus delta Z, starting from the beginning, starting from the scratch. Then you know that depending on how many sources are there internally, we have to solve this circuit those many times for each individual sources and then add the solution. Right? That's how we can do it with superposition. But here you see that all the sources are gone, internal sources are gone, and there is only one source. So it's like solving this circuit once is required in this case, whereas in this case, if we are using, for example, superposition theorem, we may need n number of times to solve it if there are n sources inside. So this could be easier. So this you must remember. Okay. Now it's time for the proofs. Proof 1. Okay, this is one way of proving it. Okay, so let us first draw the network with the impedance equal to Z, right? That was the condition before Z was changed. The network has some current sources and some voltage sources internally, and we have already solved it once to get the current I. So this I is known. Okay, so that's what is the situation. Now we apply substitution theorem on this. So what we get? So we will have this network with its internal current source and voltage sources. There could be more than one voltage and current sources. Doesn't matter. And then here we do the substitution with a voltage source, okay, V with this side plus, this side minus, because current is flowing from top to bottom according to this arrow direction, and the value of this voltage source will be same as the voltage across this in the original circuit, which is I times Z. So this is I times Z. Now substitution theorem says that if I do this substitution and solve this circuit, the current here will be I, which is same as the original current. So this is what substitution theorem says. Substitution. Okay, and this is the situation or circuit before Z is changed to Z plus delta Z. Okay, so this is the situation before Z is changed from Z to Z plus delta Z. Okay, let's keep it aside, we'll need it very soon. Now let's look at the situation. Okay, so this is the situation before modification of Z. Now let's look at the circuit when Z becomes Z plus delta Z. Okay, so what do we have? We have the network. We have to draw this voltage and current sources again and again. These are the internal voltage and current sources, and here now I have Z plus delta Z, the new impedance. Okay, and this current is I plus delta I. This value is not known. That's what we want to find out. But this is going to be the old value plus something, some changed value. Okay, so this is the circuit when Z becomes Z plus delta Z. Now let's apply substitution theorem on this. Okay, so once again, a box, that's the network, a circle with an arrow inside, that means internal current sources, and a circle with plus minus symbol, that means voltage source, internal. Okay, cool. Now here I will apply the substitution. Okay, so I will, then that means connect the voltage source here, right? I'll do that. I'll connect it soon. Okay, and before that, what should be the orientation or polarity of this voltage source? Definitely it should be from top to bottom. So this is this side plus, this side minus. And what should be the value of this voltage source? Okay, so this should be equal to the voltage drop across this in the original circuit. So that means the value should be this current I plus delta I multiplied by Z plus delta Z. So that should be the value of this voltage source. So this will be equal to, I will have four terms, IZ plus I delta Z plus delta IZ plus delta I delta Z, all four combinations. Okay, now so this should be the value of this voltage source. right? But what I can do, instead of having one voltage source, I can actually have 4 voltage sources. 1, 2, 3 and 4 connected in series like this. That's why I didn't join this line beforehand, because I wanted to have 4 voltage sources instead of having one here, with the values equal to this is IZ. The first one is IZ, this one. Next one is this I delta Z, so I delta Z. Okay, this one will be delta IZ, delta IZ, and the last one will be delta I delta Z, so delta I delta Z. Okay, and for all of them, this side is plus, lower side is minus, upper side is plus, lower side is minus, upper side is plus, lower side is minus, for all of them. So I join these 4 voltage sources in series instead of having this one voltage source. Okay, now what will be the current here? The current will be, according to the substitution theorem, I plus delta I. If I solve this circuit instead of this circuit, according to this substitution theorem, I should get the same current I plus delta I as it was in this one I plus delta I. So I have to solve this one. But now what I will do, I will apply superposition theorem on top of this circuit to solve this one. And what I will do, that means I will apply all these sources, this in one at a time or in groups. I'll do this. I will take this network with this current source internal, voltage source internal, plus minus, and here I will take one of them, the first one, IZ. Okay, so this is one circuit, plus I will take this network, then here this current source, extremely sorry, this is already used, right? So I cannot use it. So this I will have, this I have to keep it open. Okay, this current source is already used in this one. I'm going to use superposition theorem, so this I'm not able to use anymore. Similarly, the voltage source will also be deactivated, so I'll short circuit it. Okay, so this is short circuited and the current source is open circuited. And this side I will have all the remaining 3. Okay, so one of them is already used here and the remaining 3 I will use here. So this circuit is superposition of this and this, sum of this and this, these 2 circuits. Okay, okay. And these 3 values are, let me write I delta Z, then delta I Z, and then this is delta I delta Z. Okay, right. So now I have to solve the current for this one here and solve the current here, then add these two, sum these two to get I plus delta I. So this is the unknown. But now look at this circuit. This circuit is same as this circuit. Okay, so these 2 circuits are same, right? So that means if the current here is I, the current here should also be I. So I do not have to solve it. Okay, so I know this one is I. Okay, cool. That means what will be the value here? The question. What will be the current here? And this must be delta I. Why? Because these 2 currents, when they are added up, should be equal to I plus delta I. So the I plus this thing should be I plus delta I. So that means this should be delta I. Okay, so that means if I just solve this circuit, this one is not required. Okay, so this is, so let's forget this one, forget this one, this circuit. So this is, just forget this circuit and solve this circuit. So if we solve this circuit, we will have delta I, and if I know delta I is already known, then I know I plus delta I. So it's enough to solve this circuit. This by this I mean this circuit. Okay. So to get delta I just have to solve this circuit. Right. Now see, observe this. Let me group these two together. So these two into a common voltage source. So this plus this is equal to delta I times Z plus delta Z, right? If I just take the sum of these two, this is delta I times Z plus delta Z. Okay. So now I will apply kind of backward substitution theorem or back substitution theorem, whatever you call, and let me do that here. Actually, see this. So let me use this network with this open and this one short, and here let me have Z plus delta Z, and okay, I forgot this plus minus signs, plus minus, right? Okay, then let me use this plus minus I delta Z. Okay, so in this circuit, these two circuits are similar according to substitution theorem, right? So see this voltage source, instead of, in substitution theorem we replace impedances by voltage source, says, but here we are doing the opposite thing. So these two voltage sources together, which is like this, sum of these two is delta I and Z plus delta Z, and here I replace this with this one, and this I call backward substitution. Just see, because the voltage, when delta I current flows through this, the voltage across this will be this multiplied by delta I, and it is same as this. In other words, if I apply substitution theorem on this part, I get this, and this is unaltered. This particular one, this is unchanged. This is unchanged. So this voltage source is unchanged, it's here, and these two together is replaced by this one. You see, the voltage across it is this multiplied by delta I, the same as this, delta I multiplied by this. Okay, so this is, that means this circuit and this circuit are similar. So solving this is same as solving this. So I can solve this circuit, and that's what compensation theorem says. Just see, this is compensation theorem. This is the new impedance, network is deactivated, and a compensation source is added with value equal to old current and delta Z multiplied by delta Z. You may actually look into this. So that's proved. Now let's look at an alternative proof. Proof 2. And here we will do it like in this way. This is the network with internal voltage and current sources. Here is Z originally, and the current was I. That's what we got by solving this circuit. Now from here to here, change Z to Z plus delta Z. So we got and the current also changed. Okay. Now this is the new situation. Now let's ask, can I get back my old current? Can I get back my old current even when the impedance is changed? Okay, can I get back the old current, that means I, even when the impedance is changed? Okay. Suppose this impedance is increased and therefore this current is decreased. Can I do something in this branch to get back the old current? So can I increase this current to the previous value? Yes, that's possible. If I add a source in series with this, like this, then I can get back the old current. Right? Just think, if Z just for thinking, this is only for thinking, if Z increases to Z plus delta Z, right, then I decreases to I plus delta I. Here delta I could be negative, and then I add an extra source to get more current, and okay, this I means me, then okay, then add an extra source to get more current as the previous value. In other words, compensate the increase of Z or impedance with an extra voltage source. So the name compensation theorem comes from this. So here Z is increased, so I is decreased. So to compensate this decrease of I add an extra I add an extra voltage source, something V, so that this delivers extra current and it makes it equal to I as in the original one. Now let's ask the question, what should V be? So the question, what should be the value of the compensating voltage? So that this current goes back to I and everything in the circuit goes back to the previous situation. What should be V? Okay. Now, let me call these terminals as A and B, and let this voltage here. Okay, that means between these two terminals be VAB originally. Okay, so when nothing was changed at the very beginning, let this voltage be VAB. That it was. Now here the current is first changed, and then here the current has gone back to the previous value. This is A, this is B. Now this current is I. Okay, so the network is delivering the same amount of current I. That means here the voltage between these two terminals should again be VAB. Okay, so this should again be equal to VAB, which was same as this. So here VAB, this was equal to I times Z. So here once again, so this value should be equal to I times Z. Why? Let me repeat. Because the network is delivering same amount of current externally, so the network should see the same amount of voltage here, same amount of voltage between these two terminals. Because the network has some VI characteristics, I don't know how it is, the network may have some VI characteristics. So this is VI characteristic of network, which means for a particular amount of current being delivered, the voltage should be of a particular value. If this is my current, this should be the value, should be the voltage, and that means when it's delivering same amount of current, no matter whatever there outside externally, the voltage here should be same. No matter you have an impedance, have a voltage source, whatever it is, if the network is delivering same amount of current, the voltage that should appear across these two terminals should be same. That's equal to the voltage as it was here. Because here it is I, here it is I, so here if it is VAB, this also should be VAB. Now VAB is, here it is IZ, so here also, in this circuit also, VAB is IZ. Okay, so this is I times Z. Now what is the value, what is the voltage drop from here to here? this is equal to I multiplied by Z plus delta Z, that's the impedance, and then plus V for this voltage source. So that's the voltage drop. Now this should be equal to VAB, which is equal to IZ. Okay, so if so, from this we can find what V should be. So this means V is equal to IZ minus IZ plus minus I delta Z. Okay, so that means V is equal to minus I delta Z. So what does this say? This says that if you apply this voltage source like this, then you will have the current restored to the old value. And if you do not have this voltage source V as it is here, then the current will be I plus delta I. So that means this current is delivered by the internal source of the network. So this is delivered by network. Okay, this one, and this one is delivered by network and V. Okay, so this current I is being delivered by the network and V, because now both these are on, right? So that means, let me ask then, what is the current delivered by V alone? So that's the question. Okay, so we'll use superposition. See, so V delivers, sorry, network delivers I plus delta I, network plus V delivers only I. So that means V delivers how much? This minus this, I minus this, I plus delta I, which is equal to minus delta I. Okay, so V alone will deliver this much of current. So that means if I draw this network with only V, let me redraw this network. With only V, so current sources are opened, voltage sources are sorted, and here I have Z plus delta Z, Z plus delta Z, and here I have V plus minus V, where V is equal to this minus I delta Z. Then this current will be minus delta I. Why? Because this circuit is a superposition of this circuit and this circuit. Just see. So let me call it circuit, this circuit A. Let me call this as circuit B, and this as circuit C. Now, according to superposition, we see that circuit A is equal to circuit B plus circuit C. A with everything on is equal to B with the internal sources only, and C with the external source only. Okay, so this one delivers minus delta I, B delivers I plus delta I, so this one delivers the sum of these two, which is I. Okay, so if I have this circuit, I will get minus delta I. If so, now the next step is obvious. This is a linear circuit, linear network. There is no other voltage source inside. So instead of this minus, if I just replace this minus with plus, and this, then definitely this current will become plus. I'm just reversing the voltage, polarity of the voltage, so the current should also be reversed, because now this is a completely passive network. There is no other source, so that should happen. So that means, what does that mean? If I apply this voltage, then I will get the current which is equal to delta I. So if I want to find delta I can solve this circuit. So to find delta I, just solve this circuit C, and that's what compensation theorem also says. So let's just go back. That's what the compensation theorem says. Just deactivate this network, say it's deactivated, put V equal to delta Z times I here, and then the current that you get is delta I. That's it. Now I will give another proof, which is the easiest one, I believe, proof 3. And here I will use just Thevenin's theorem. Okay, and this is the easiest way to remember the compensation theorem. Okay, good. And the previous one, this particular proof, actually is from where the name compensation theorem comes, because we ask the question, if this current is reduced by the increment of this impedance, can we add an extra compensating voltage to get back the old current? That's it. Now let's come to the Thevenin's theorem. Thevenin's theorem based proof. Okay, so this is my network. This is easiest proof. Network, here I have Z, here I have the internal sources. This current is I, and when I change it, like this, Z plus delta Z, this becomes I plus delta I. Now let's assume that the Thevenin voltage between these two nodes is VTH. This is equal to V open circuit of for the network, and ZTH equal to internal impedance of network. If so, what I can write I is nothing but VTH divided by Z plus ZTH from this circuit, And from this circuit I can write I plus delta I is equal to VTH by Z plus delta Z plus ZTH. Right? Now what? Now this VTH, let me eliminate VTH. So I will take a ratio of this two, and I will have, let me do this, that I plus delta I divided by I, that means this by this will be equal to then Z plus delta Z plus ZTH, and here I will have Z plus ZTH. Okay, cool. Now I want to find basically delta I. Now let's cross multiply and see what happens. So I will have I times Z plus ZTH, Z plus ZTH, and plus I times delta Z. Okay, so I'm just cross multiplying this, plus delta I plus delta I times Z plus delta Z plus ZTH. So this is this multiplied by this. Okay, I times Z plus ZTH and delta Z, and delta I times all three. Okay, now this is equal to I times this, I times Z plus ZTH. Right, now you see this and this cancels. So what I am left with is this, that delta I is equal to minus I delta Z divided by Z plus delta Z plus ZTH. That's it. So our delta I is minus I delta Z by this. Let me put a bracket which will be useful later. Okay. Now this looks like Thevenin's theorem. Okay. So this looks like something like current I equal to some VTH no, it's not like Thevenin's theorem, sorry. But okay, this is of the form that, I mean, some current is some voltage divided by this impedance. Okay, Z plus delta Z plus ZTH. Okay, let me call it delta I as it is. So actually this immediately suggests that this current can be found, this current delta I, so this is the unknown, okay, right? So this unknown can be found if we apply this voltage across this impedance. Okay, so let's look at this circuit. Okay, let's look at this circuit now. Okay, so what is the impedance of this circuit as seen from these two terminals? This is ZTH. Now in series to this I add Z plus delta Z. Okay, so ZTH, this one is ZTH, and Z plus delta Z is I'm adding in series. Okay, and then I'm applying a voltage which is equal to minus I delta Z. Then let me take it in this direction. Okay, so any direction you can start with. Okay, So now that means if I apply, see, this voltage across this circuit, what will be the current? Ask this question. What is this current? This current is nothing but this, right? This voltage divided by this impedance, which is Z plus delta Z plus ZTH. That is this current. Okay, and this is actually in, if this is plus, so this is in this direction. Okay, so this current is this, minus is this, right? Now I have to fix the directions. Okay. And this quantity from here is delta I. So this is delta I. So that means if I apply this voltage here, the current will be this, or which is equal to this. So this current will be delta I. So this will be delta I. This current is delta I when the voltage is this. Now let's just change the polarity. Let's make it plus, and therefore if I make it plus, the current will flow from, instead of left to right, it will flow from right to left. So let me erase this and put an arrow from left to right. Okay, so that's what we got. So that means if we apply this voltage across this circuit, we will get delta I. Okay, so that's it. And that's what compensation theorem says. So we have proved compensation theorem using Thevenin's. So using Thevenin's theorem, we have derived compensation theorem.